So today we're going to talk about relative motion. So relative motion occurs when both an object and an observer both of them are in motion. So the motion to the moving observer would be different than the motion to a fixed observer. Just equations for relative motion. So for velocity, the velocity of object B is equal to velocity of object A plus B relative to A, which means that velocity B relative to A is equal to VB minus VA. Acceleration is much the same. So B relative to A is B minus A. So in this case, A is the moving object and B is the moving observer. This equation holds even if the components are negative, so you just put the negative in there. And it can be generalized into 2D and 3D as well. So usually we look at relative motion in terms of velocity and acceleration. So velocity, relative velocity is fairly easy to visualize. It's just the difference in acceleration between one object and another. So you want to think about a person moving through a train, for example. So their velocities will either add or subtract to give the velocity of the train perceived by the observer. And acceleration is a bit less intuitive. So acceleration must have a normal component if the path is curved. That's something we have to remember. And it's just a bit less intuitive because it's hard to visualize relative acceleration. So procedure for relative motion. First, we want to write the vectors, so velocity and or acceleration, in normal tangential component form. And then we want to translate into x and y components from normal tangential using trig. We know how to do that from previous lessons. And then we want to write the vector equation. So velocity of A relative to B is equal to velocity A minus velocity B. Also works with acceleration. And then we want to add the components to get the total magnitude, and finally find the direction using trig or ij components. So just some other tips. We want to draw the vectors relative to a fixed origin, and then write separate equations for each component. We should also make sure at the end and as we're going through it that we check the sign of every component with regards to the diagram. So for the example today, we're going to do one that's a little bit trickier just in terms of visualization. So it is relative acceleration. So we can see the diagram there. A bit poorly drawn, apologies for that, but we'll do this example relative to that diagram. And then there is the extra example as well, which is a little bit easier because it is relative velocity instead of relative acceleration, but we're going to start with this one first. So we're going to look at car A. So the acceleration of A, and I'll go ahead and split this into components right away. So the acceleration of A in the x component is 0 because we know that it's traveling straight north or straight up. It does depend on how you define your coordinate system, but in this case we'll just use the sort of the normal coordinate system, and I'll just write that down here. So positive in the y direction is up, and positive in the x direction is to the right. Okay, and then we have the acceleration for A in the y direction, which is simply 3 meters per second squared. Okay, so then we're going to look at car B, which is a little bit more involved. So we'll look at it in terms of normal tangential and then turn that normal tangential into x and y components. So normal acceleration is the velocity over the radius of the curve. So in this case, the velocity was stated at 20 meters per second. squared over 100, which is equal to 4. And tangential acceleration was stated in the question, which is just equal to 2. So what we're going to do with this is we're going to find the magnitude of the acceleration. So that would just be 4 squared plus 2 squared, which comes out to be 4.47 meters per second squared. And then we can find the angle relative to the tangential acceleration. So if we have the car, sort of like this, then this would be the tangential acceleration. This would be the normal acceleration. And that would, something like that would be our combined acceleration vector. So that would be the total acceleration of b. So what we want to find here is this angle here, because once we find that angle, then we can add it to, or subtract it rather from that 30 degrees, because remember, this comes down, and we'll call this one theta equals 30. So if we subtract 5 from theta, then we will be able to define it more in terms of x and y components. Anyway, we'll get to that a little bit. So we can say that phi is arctan of normal over tangential, and so this would be equal to 4 over 2, which is 63 degrees. And we have theta minus phi is negative 33 degrees. So then that means that sort of what we're looking at, if it's on a Cartesian graph here, then this would be 33 degrees, which means that this would be 67 degrees. This is all to say, 57. This is all to say that the acceleration of car B is 57 degrees above the positive x-axis. So it just takes a little bit of geometry there. So then we can find the x and y components of the acceleration of B. So the x component would be 4.47. So the magnitude there, times the cosine of 57 degrees, which would equal 2.44. And then similarly for the y, we'd have 4.47 sine 57 degrees, which is equal to 3.75. Okay, so now we have the acceleration of A and acceleration of B, both in terms of x and y components. So what we're going to do is we'll find relative acceleration. So acceleration of A relative to B is equal to acceleration A minus acceleration B. And I'm going to do this in ij components. So we have the x component of A is 0 minus the x component of B, which is 2.44. I plus, and then we have the y component of A, which is 3, minus y component of B, 3.75. So then acceleration of A relative to B would be negative 2.44I minus 0.75J. And we can go ahead and further find just as a total acceleration and the angle there. So the magnitude of acceleration would be 2.44 squared plus 0.75 squared, all square rooted, which would be 2.55 meters per second squared. And then the angle would be tan, inverse tan or arctan of negative 0.75 over negative 2.44, which would give us 197.1 degrees with respect to positive x-axis. And that makes sense because we know that so the x, so for relative acceleration, the x is negative and the y is negative, so it would have to end up somewhere in that third quadrant, and 197 degrees would be in that third quadrant. So okay, so then we can state that acceleration of A relative to B is equal to 2.55 meters per second squared, 197.1 degrees counterclockwise from positive x-axis. Okay, so that's how we do that question. This is the end of the video now, so take a look at the extra example, as well as this example annotated, and the PowerPoint will be shared in the description below, so just click on the link. And thank you again to Loom and Google Keep and as well to my professors. I hope this helped, and we'll see you again next time.